The basic idea is this. When you have a geometric object, you want to find simpler mathematical ways to understand that object. And the kinds of questions that you want to ask might be, how does this part of the object intersect with this other part of the object? So in order to study that, you associate to your complicated geometric object, something simpler. The same way that we might take a moment map to associate a complicated geometric object to a polytope, we could also take that complicated geometric object and associate to it some kind of algebraic thing. So by algebra, I mean things like polynomial rings. When we talk about polynomials, they can multiply together, you can multiply polynomials, you can add them, you can ask questions about them. So Schubert polynomials are the polynomials are representing geometric things about a certain class of very complicated objects, which we call flag manifolds. But it doesn't really matter what the complicated objects are, because in some sense, when you get to the polynomials, you've got complicated algebraic questions to ask by itself. So the correspondence comes from very subtle, sophisticated mathematics. But once you have the correspondence, you can say, okay, if I want to study this geometric object over here, I can move over here and study this algebraic question that somehow will answer what I wanted to know about my original geometric object. So the kinds of questions that I'm interested in are, take your complicated geometric object, intersect certain parts of it, and what do you get when you intersect them? And the way we translate that over to algebra is we say, well, here's some Schubert polynomials. How do they multiply together? And the answer to how they multiply together turns out to correspond to the original geometric question.